Hi everyone, I'm Jiahong Ouyang from Stanford University. Today, I'm going to present our work, Representation Disentanglement for Multimodal Brain MRI Analysis. Multimodal MR is widely used in neuroimage applications, as different MR contrasts can provide complementary information on brain structures. However, using multimodal MR usually encounters into incomplete input problem due to the data corruption, especially when using large datasets. Existing work have shown that one solution to this problem is by disentanglement. Let's first define what's the disentanglement we talk about. A MR image can be encoded into two parts. The first part is modality representation. It captures the appearance of the modality. This appearance is shared among subjects, but different across contrast. The second part is anatomical representation. It captures the brain anatomy. For the modalities from the same subject, this anatomy is shared across modalities, but different across subjects. So how this disentanglement can help the incomplete input problem? We can first get the disentangled anatomical representation, and then based on this, to get a representation that is invariant to the missing modality. Existing works have also shown that the disentanglement can also benefit multi-domain image synthesis, deformable registration, multimodal segmentation, and image harmonization. In this work, we first propose a better disentanglement method. It consists of two parts, a normal similarity loss and a modified conditional convolution layer. The disentanglement is evaluated by a cross-reconstruction quality and the visualization of the representations. Next, we propose a framework for using disentangled representations for missing modality scenario. It's achieved by using a fusion module to get modality invariant representations. And this part is evaluated by two downstream tasks, zero-dose PET reconstruction and brain tumor segmentation. Before we introduce our method, let's first have a look at the existing disentanglement methods and their limitations. The first type of the method is achieving disentanglement by cross-reconstruction. The main pipeline is like this. Here are two MR contrasts, I and J, from the same subject. Each of them goes through a modality encoder and an anatomical encoder to get the modality representation Z and the anatomical representation S. This Z and S can be mix and match, and then go through a decoder to achieve the cross-reconstruction. This type of method attempts to achieve the disentanglement by localizing the cross-reconstruction loss. But the problem of this type of method is obvious. It does not explicitly regularize the disentanglement. Also, usually this method uses separate decoders for each modality. And this can lead to a problem that the anatomical representation can still carry some modality information, as long as the decoder is good enough to remove this information. Based on the first type of the method, here comes the second type, disentanglement by adversarial training. a discriminator is added to distinguish which modality the anatomical representation S comes from, and an adversarial loss is added to foil this discriminator. But the problem of this type of method is that, first, the adversarial training can be very unstable. Also, only the anatomical representation can be adversarial regularized. It means that the modality representation can still carry some anatomical information. And also, the separate decoder problems remain unsolved. And there are some concurrent work at the same time can be summarized as the third type. They try to achieve disentanglement by mutual information. In this method, the mutual information term will be reorganized as a KR loss in variational models. But the limitation of this type of method is that it's hard to regularize a high-dimensional representation, so it limits its usage for the downstream tasks. So here is the question. Are these so-called disentanglement methods achieved real disentanglement? The answer is no. This method usually use cross-reconstruction quality as the metric to evaluate the disentanglement. But as we discussed earlier, there can be information leak between representations, even with good reconstruction. So we need visualization of the disentangled representations. And here come our proposed method. Here, xi and xj are two MR contrasts from the same subject. They go through the modality encoder to achieve the modality representation z, which is a 16-dimensional vector. At the same time, xi and xj go through the anatomical encoder to achieve anatomical representation S. And in our method, S is a 4-channel feature maps of the same size as the original input image. The first loss component is the reconstruction loss. A pair of S and Z are fed into the decoder to get the reconstructed image X tilde. When S and Z are mix and match, it's the cross reconstruction. When using S and Z from the same modality, it's the self reconstruction. The second component is latent loss. We further put the reconstruction image through the modality encoder again to get the Z tilde. A loss term is added to encourage this Z tilde to be close to the original Z, so that we can ensure that the reconstructed image is in the expected modality domain. And here comes the most important part of our method. We design a margin-based hinge loss to enforce better disentanglement. This loss is designed based on the similarity between representations, and is measured by the cosine similarity. In more detail, here we have two modalities, I and J, from two subjects, P and Q. Let's first talk about the anatomical representation, S. The anatomical representation from the same subject, different modality, is labeled by the red color, and it should be more similar than the anatomical representation from the different subject in the purple color. And as shown in this equation, we hope the red pair has higher similarity than the purple pair by a threshold alpha s. Similarly, there is a coupled term for modality representation Z. We hope the modality representation from the same modality different subject in the purple box is more similar than those from the same subject, different modality, that's in the red box. And we hope that the purple pair has higher similarity than the red pair by the threshold alpha z. Moreover, we propose a modified conditional convolution layer to enable one set of encoders for all modalities. Comparing to traditional convolution that only have one set of parameter w, here we have n set of w, and we have a beta to weight these w's. The beta here is a set of modality-specific mixture weights that is adaptively learned by a linear layer. By using the modified conditional convolution layer in the encoders, we can improve the computational efficiency and also potentially learn better model by sharing weights between modalities. In the next part, we propose a fusion module to utilize the disentangled anatomical representations for downstream tasks. Here, we fix the encoders from the disentanglement. And in the first row is the anatomical representation from 4 modalities. One of them is missing in input. And in the fusion module, we use max pool, mean pool, and average pool across modalities, and concatenate the pooling features together as the output of the fusion module. This concatenated feature should be invariant to the input modalities, as the anatomical representation does not include modality information. And also, this concatenated feature can be used as the input for any state-of-art downstream task model. We evaluate our method on 3 datasets. The first one is Incanda. It consists of T1 and T2 MRI from 692 adolescents with no to low alcohol drinking. The second one is zero dose. It consists of T1, T2 flare MRI, and their corresponding FDG PET images, and is from 171 subjects with multiple diagnoses, including tumor, epilepsy, and dementia. The downstream task on this dataset is trying to synthesize PET images from multi-contrast MRI images. In the last dataset is breadth. It consists of 4 MR contrasts, T1, post-contrast T1, T2, and T2 flare MRI, and their corresponding segmentation mask. It's from 369 subjects, all with brain tumor. The downstream task on this dataset is brain tumor segmentation. We compare our method with 2 types of existing methods. Plus NA means disentangled by cross reconstruction. Plus ADV means disentangled by adversarial training. And plus SYN is our proposed method. Also, we use conv denotes training separate encoders for each modality using traditional convolution, while count-conv denotes training a single set of encoders by the proposed modified conditional convolution. Here, we first visualize the modality representation in a 2D space. The dots are color-coded by modality, and a well-disentangled modality representation should be clustered by modality and shouldn't have mixture between modalities. And it's just like our result in this plot. Well, as we can see in these 2 plots, the modality representation by competing methods are mixed together. It suggests that there are some anatomical information leaks to the modality representation. Similarly, we can also plot the anatomical representation in 2D space. Color still denotes the modality, and we select 4 adjacent slices from 4 randomly selected subjects. Different marker shape labels different subjects. As each subject has different anatomy, there should be 4 clusters by 4 subjects. But just like this plot shows, a well-disentangled anatomical representation, there should not have modality bias within each subject's cluster. And here, as shown by the small circle within the cluster, competing methods both have modality subcluster within each subject's cluster. And it suggests that there are some modality information leaks to the anatomical representation. In this page, we further visualize the 4-channel anatomical representation S. And here is a subject from Incanda dataset. For disentangled anatomical representations, the corresponding channel from different modalities should be visually similar. And as we can see, only our method achieved this, while the competing methods looks distinctively different. We then evaluate the disentanglement by cross-reconstruction quality. And here is a visual example from Brett's dataset. Different combination of S and Z makes a 4x4 image matrix. As highlighted in the red boxes, using the proposed similarity laws achieve visually better cross-reconstruction quality. We further show the quantitative result of cross-reconstruction on Brett's dataset, and is measured by PSNR. In the red boxes, we can see the proposed similarity laws help to get better cross-reconstruction quality than competing methods on all 4 modalities. We also highlight that using conditional convolution can achieve similar or better quality than using the traditional convolution. In this page, we show the result on the downstream task. On the left is zero-dose reconstruction measured by PSNR, and on the right is brain tumor segmentation measured by DICE score. Here we compare with 2 widely used image imputation methods. Standard plus 0 means using the original image as the input, while using all 0 for missing modality. While the standard plus AVG means using the average image for the missing modality. And in the red boxes, we can see when there is no missing modality, our method achieves similar performance as the standard method. And in the red boxes in this page, we can see when there is a missing modality, our method achieves significantly better performance. In conclusion, we first propose a method for better disentanglement. It consists of a novel loss based on the cross-subject and cross-modality similarity, and a modified conditional convolution for computational efficiency. We evaluated it by visualizing the disentangled representation and the cross-reconstruction quality. We then propose a way of using this disentanglement for downstream tasks with incomplete input. A fusion module is introduced to achieve modality invariant features. We evaluate this part on the downstream task on 2 datasets. At the end, I would like to thank to my colleagues from Stanford Computational Neuroscience Lab and Stanford Center for Advanced Functional Neuroimaging. Thank you all for listening, and I'm looking forward to discussing more during the conference.